Let's record. Okay, so today, again, what we're going to start with is just this, is just this last way of representing structures, right? So each of these things represent the same sort of piece of information, the structure of these organic molecules. And again, structure is going to be a super important part of this course. A lot of what we understand about chemistry of organic compounds has to do with its structure. So we're going to learn one more way to represent structure, and that is this condensed formula here. So something like CH3, CH2, CH2, CH3. Okay, this would be the condensed. What do they call it? Structural formula. The difference between the condensed and the structural formula is in the structural formula, you're explicitly showing all of the bonds. So I would have, so if I did this exact same molecule, right, I have 1, 2, 3, 4 carbons in there. Doing the same thing as a structural formula, I would explicitly draw all my 4 carbons. And then we also learned about the bond line. Everybody take a second and see if you can't give me the bond line structure for this compound here. Remember, that's just those where you're implicitly representing carbons and hydrogens. Carbons are at endpoints and intersections, and the hydrogens are just kind of implied based on how many bonds carbon needs. Okay, so for 4 carbons, I would have, this is 1, 2, 3, 4. So that would be my bond line structure. Again, all these have that same bit of information in there. Again, you can see why the bond line structure is preferred in the sense that it's just so convenient. It's so quick, right? So it does take a little bit of knowledge. It does take a little bit of interpretation, but it's so much faster to draw structures when you're using the bond line formula. Okay. So again, the new one here is our condensed formula. This is something that, you know, textbooks and stuff like, because they can put this formula all in one line. For like simple alkanes and stuff like that, it's pretty straightforward. Things get a little bit more tricky. So for example, if we had CH3, CH2, let's do, oops. Compared to CH3CO. Okay, so importantly, again, when you're kind of interpreting your condensed structures, the most important thing is we stick to those simple rules of carbon needing 4 bonds, oxygen needing 2 bonds, nitrogen needing 3 bonds. So these structures are very, very similar, right? I have the same 3 carbons. I have 1 oxygen in each, but they're going to lead to different structures. And you know, if you're playing the spot the difference game, the difference is this hydrogen here, or these 2 hydrogens I have in my one condensed formula and not in the other one. So what you're going to do is you're just going to kind of start reading it off from left to right and building this molecule. So this first one is telling me that I have a carbon with 1, 2, 3 hydrogens attached, right? So that takes care of this portion here. Then I'm going to move on to the next one. I have a carbon, and this one has 2 hydrogens attached. So that takes care of that chunk. My next one's an oxygen. Since this carbon, this one that I colored in yellow, already has 3 bonds, that's just going to go there. And then I'm going to put my last carbon That's represented there. Okay, so when I'm going from my condensed formula to my structural formula, I'm just going to make sure that everything has that complete octet. Everything has the correct number of bonds. If we go down here, we start off the same, right? So I'm starting off with a CH3. What did I use? So here's, oops. So that's that chunk there. I then have my next carbon here. Notice that this carbon does not have the correct number of bonds yet, right? It only has one as it's drawn. So when I jump to that next oxygen, that's going to have to be onto that carbon with 2 bonds in order to create, you know, 4 bonds for that particular carbon, followed then by the CH3. Okay, so how you put these things on are all just going to depend on that same sort of simple set of rules for drawing structures correctly, where you're making sure that everything has the correct number of bonds. In particular, you're like looking for how many hydrogens follow the carbon label. Okay, because that'll tell you, okay, this needs to be, for example, this double bond here as opposed to the single bond in the structure above. The other thing is, truthfully, you just get good at spotting common patterns. So something like CH3COOH. The COOH is something that we're going to learn is called a carboxylic acid, but that looks like this. There's my CH3, COOH. This is just like a signature for this functional group here. We haven't really learned about our functional groups yet. We're just learning how to represent molecules, how to draw them. But you'll see like little codes that will always correspond to particular things. So for example, COOH will be that there. If you have something like CH3COO and then another set of carbons, that's going to correspond to something very similar, but OOCH3. Okay, so again, you have that kind of like COO signature in there. And so truthfully, that's how I sort of learned to get good at reading these sort of things, is just by spotting these similar patterns that you see over and over and over again. I think that the carbon double bonded to the oxygen is the hardest one to see from the formula. That type of bond, we call it a carbonyl bond, is really important in organic chemistry. So we will see it over and over and over again. Some of the other ones are much easier to spot, like CH3CH2OH, CH3CH2NH2. These ones are a little bit easier to sort of understand. I think mainly just because there's only one carbon oxygen or carbon hydrogen bond. Okay. So anyway, these are our condensed formulas where we're representing these structures just in one simple line here. It's a great way to kind of quickly convey the information. Typically, when we're doing reactions and stuff like that, we'll actually go for the full bond line structure or something like that, because we want to be able to point to bonds and all that good stuff. But nonetheless, we want to be able to recognize when a structural formula corresponds to one of these condensed formulas. Okay. So let's just do a little bit of practice here. Oh, Actually, let's do this. How about you guys give it to me for this one? All right, so take a second and go from our condensed formula to a structural formula, and then from this structural formula to the condensed formula.
The last symbol is chlorine, right?
Yeah, that's chlorine.
All right.
Or it's trying to be. Okay. So the CH3s you'll spot pretty easily. Those always indicate like an end point or a terminal carbon. CH2. And then we get to this carbon here. And notice how there are no hydrogens associated with that carbon. That's the signal that I'm going to have to use this double bond for that oxygen. Because otherwise that carbon, right? If I did something like this, I could spot that that was wrong because all of a sudden I have this carbon that doesn't have a complete octet. It doesn't have the correct number of bonds. So it's okay to do a little bit of trial and error, you know, put something down, double check it, make sure it makes sense. Again, you'll get good at just kind of like spotting little signatures. And then here, this carbon has 2 hydrogens, and the last thing is going to be that chlorine, that's Cl. We're going to see these halogens do play a common role in organic chemistry. It turns out that these types of molecules are really reactive. So they're great starting points for reactions. If you want to create a molecule, if you start with one of these halogen containing compounds, they're really easy to turn into other things. We're not there yet. Again, I think one of the most intimidating things about organic chemistry, kind of chemistry in general, but definitely organic chemistry, is everything seems so infinite, right? So you look at something and you're like, how the hell, I'm supposed to understand all these reactions and all these blah, 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 blah. It's important to know like what step we're at in the course. Right now, we're just drawing structures. We don't know anything about these molecules whatsoever. We don't know how to name them. We don't know their reactions. We don't know their boiling points. We don't know any of that stuff quite yet. We're just focusing on making sure that we can draw these structures correctly to accurately represent these molecules. And we have 3 different ways to do that that are kind of equivalent. You know, they look differently, but they convey the same information. The condensed formula, which is the one that we're just doing now, where you run it all into one line. The structural formula, where you're drawing all those bonds explicitly. And then the bond line, the one that I really love because it's so easy, where we can convey all that same information, but really, really quickly in a sketch like that, right? All these are just 3 different ways of representing organic molecule structure. We don't know anything about them yet. So don't like get ahead of yourself in terms of your confusion, right? I mean, it's okay to be confused about not knowing what the heck it is because we're not there yet. All right, so for this one, how we would do it in a condensed formula. Again, we're just going to read from left to right here. Starting out, we have a CH3, then a CH2, then an NH, followed by another CH3. Okay, and if I wanted to represent this as a bond line structure, Remember, the nitrogens are going to be explicitly represented, right? So 1, 2, then I get to that nitrogen. So I'm going to explicitly draw that in. Notice that you also explicitly draw in the hydrogen that's bound to that nitrogen, right? So because it's not a carbon, nothing's implied anymore. You have to draw it in explicitly. And then I have my last carbon as well. Okay, so 3 different representations of in this case, these same 2 molecules. Okay,
So
cool. What's up?
For nitrogen, the hydrogen is not implied when you're doing the line.
Yeah, for any sort of like what we would call a heteroatom, meaning it's not carbon or hydrogen. And really the ones that you're going to see over and over again are oxygen and nitrogen. In those cases, you have to draw the hydrogens explicitly. So for example, an alcohol, something like something like this with an OH group, you would draw the O and the H explicitly. Okay, because let's remember, if we leave off that hydrogen, this is also sort of saying something different. Remember, what do we know about an oxygen that only has 1 bond? Everybody in the chat, what do we think the formal charge is on an oxygen that only has 1 bond? Let's remember we built a little cheat sheet last time. Remember, the number of bonds corresponds to the formal charge on those molecules, or on those atoms rather. If we're talking about oxygen likes to have 2 bonds, nitrogen likes to have 3 bonds. Well, what we mean when we say it likes to have is that would give those atoms a formal charge of 0. Anything less than that, and it will have a negative formal charge. So if oxygen only has 1 bond, you're representing that it has a formal charge of -1. And if you draw that oxygen with 3 bonds, or that nitrogen with 4 bonds, 1 over what they like to have, you're representing a structure where it has a positive formal charge. As you can tell, I don't really like our textbook's lecture slides, so I'm kind of doing my own thing here. So anyways, when I'm drawing this oxygen like naked like this, without a hydrogen on there and only 1 bond, I'm implying that it has a formal charge of -1. Okay, and I can also fill in lone pairs, right? So take a second and fill in lone pairs on each of these 2 structures here. Right, so if oxygen has 2 bonds, then it has 2 lone pairs. If it only has 1 bond, then it has a formal charge of -1 and has 3 lone pairs. Okay, so last sort of skill with our structures that we're going to learn, and this one's kind of a doozy, but it's also really cool. So if you think about a chemical reaction is all about making and breaking bonds, right? You start out with 2 reactants. There are bonds that are broken and then new bonds that are formed. Okay, and bonds are made up of what? These are electrons. Okay, so if we want to understand a chemical reaction, we want to understand how the electrons are moving in a reaction. Okay, like we know that atoms consist of protons, neutrons, and electrons, right? Turns out the protons and the neutrons aren't really doing crap. They kind of just sit in the middle of that atom and they hold the electrons there. But the electrons are the interesting part. They're the ones that are creating the bonds. So they're really the ones that are driving chemical reactions. So we have this way of representing the movement of electrons, and that's called electron pushing arrows. Okay, so I think up until now, maybe, we've seen our Lewis structures before. The bond line structure was probably brand new. But I think, again, like everybody's kind of seen a hexagon being associated with organic chemistry. These electron pushing arrows are also going to be kind of like brand new information, something that looks a little bit weird at first. Okay, so just bear with me here. I know it's going to be a little bit challenging. By the end, we'll get the hang of it. So remember, when we had our Lewis structures, we could have something. So for example, if I wanted to draw the Lewis structure for the nitrate ion, I actually have to draw, let's actually do a simpler one. Let's do the nitrate ion, NO2 minus 1. You actually have to draw two structures that are in resonance with one another. Okay. Everybody take a second and put in the lone pairs as well. Again, the number of bonds that oxygen have will sort of imply how many lone pairs it should have. So when it has two bonds, that's two lone pairs. One bond should be three lone pairs, and that formal charge. Okay, so when you're drawing the structure for the nitrite ion, I mean, really, like, first of all, take a step back. We play spot the difference here. The difference is where this double bond is located, right? You can draw that double bond on either oxygen. So instead of like arbitrarily picking one, you actually have to draw both. Okay. So if we're going to go between these two resonance structures, this pair of electrons is going to be moving. All right, so that's what our electron pushing arrows are going to allow us to do, is to represent the movement of that electron, those electrons. Okay, so it's actually this bond here. So for right now, again, we're brand new to this. Just kind of trust me, make sure that you can follow along with, with what it is I'm saying. Don't worry about being able to do it from scratch yet, right? So for right now, just kind of try to understand where I'm going with this, sort of see that these arrows represent the movement, and then we'll work on getting to the point where you can draw them all on your own. Okay, but for right now, we're brand new at this. So this bond here that I represented in pink is going to come from this pair of electrons here moving down. Okay, and so how I'm going to represent that is with one of these electron pushing arrows, which are always curvy arrows. The base is going to be starting at the electrons that you're grabbing, and you're moving them to a new location. Okay, so that's what our electron pushing arrows are doing. This is kind of the picture that I have in my mind when I'm drawing them, is I'm grabbing this pair of electrons and moving it somewhere. So if I'm going to grab this pair of electrons in pink here and move it down to form that bond, I'm going to do that there. And that, again, is grabbing that pair of electrons and moving it down to form that new bond. Now I can't stop there because I have this bond over here that isn't on the other side, right? So again, just the spot the difference game. I'm going to grab that pair of electrons that's in that bond. So first of all, let me just show you. It's going to move up here onto this oxygen. So I'm going to grab that pair of electrons from that bond and move it up. Actually, I can make this more clear by moving this pair around. Grab this pair of electrons and move it on to that oxygen. Okay, so again, we have these electron pushing arrows. The base is where the electrons start, and then the tip of that arrow is where the electrons are going. Right, and again, what I want you to have in your mind is this idea that you're grabbing this pair of electrons and dragging it into a new location. Okay. So let's do a bunch more examples here, because I know this is a very common sticking point. What we're going to see is it's really cool because when we do a chemical reaction, we can show where the electrons are moving in that chemical reaction. We can show where they're moving when bonds are breaking and where they're moving when bonds are formed. But I know this is a really tricky thing, so we're just going to go through and practice it a bunch today. Okay. So for example, let's take something like this. We want to convert this to this with our electron pushing arrows. Real quick though, go ahead and put in the formal charge and the number of lone pairs on the oxygen in each of these structures. Right, because again, just by drawing an oxygen with 2 bonds, I know how many lone pairs it has. When I draw an oxygen with 1 bond, I know how many lone pairs it should have. So this is just a standard oxygen, so this should have 2. This is an oxygen with only 1 bond, so it's got a total of 3 and a negative charge of -1. Okay, and this carbon actually with only 3 bonds will have a formal charge of +1. We can add another little table. For now, I want to focus on the electron pushing arrows, but yes, carbon likes to have 4 bonds, remember? So if it has 1 less than that, it's going to have, actually, it gets a little weird. So actually we'll use our formal charge equals number of valence electrons minus number of electrons in the structure. In this case, carbon has 4 valence electrons based on where it lives on the periodic table, and it only has 3 here. So that's how we got a formal charge of +1. Unlike hydrogen and oxygen, carbon's allowed to sort of violate that octet rule. So it's only got 6 electrons in its octet right now. This structure that I draw is not like a super stable structure or anything like that. It's actually quite unstable, but nonetheless, we can use our electron pushing arrows to get from one of these to the other one. And again, the first thing we're going to do is play the spot the difference game. Right, so in this particular structure, I have 2 bonds, and in this one, I have 1. So I know I'm going to be breaking this bond here. I know I'm going to have to get rid of a bond on the left-hand side. And likewise, on the right-hand side, I have this extra pair of electrons here. Right, that's not on the other side. So I can represent this by moving that pair of electrons up onto that oxygen atom, right? I'm grabbing that pair of electrons that was in that bond and pulling them up so that they're associated only with that oxygen. Okay, let's do just a bunch more here. A big part of this course is going to be acid-base reactions. Remember, acids are proton donors and bases are proton acceptors. So a common base would be the hydroxide ion. A common acid would be HCl, hydrochloric acid. And if these two react with one another, you would get a chloride ion and water, H2O. Okay, so this would be an acid-base reaction, one of the first ones that we would have learned, you know, in general chemistry between a hydroxide ion and hydrochloric acid. We're going to go in and fill in with our lone pairs of electrons. This oxygen has a negative charge, so it would have 3. This on the right-hand side has 2 bonds. It doesn't have a formal charge, so there are only 2. And we'll go in and fill it in for our chloride as well. The halogens have 3 lone pairs. When they have that negative charge, there would be 4. Okay, so we can represent this chemical reaction. We can show what electrons are moving here using these electron pushing arrows. All right, so again, first thing that we're going to do is just kind of play the spot the difference game. Over here, I have this bond that doesn't exist on the left-hand side of this reaction. So I'm going to have to create that bond. That bond is going to be formed in this chemical reaction. Likewise, I have this bond here that I don't see on the right-hand side of my reaction. So I'm going to have to break that bond. Right? Chemical reactions, if we're going to like dumb it down and make it really simple, chemical reactions are just the making and breaking of bonds. So, and I got to break some bonds and I got to make some bonds to represent this chemical reaction. This new bond here that's formed is between oxygen and hydrogen. So how I would represent that, let me use my colors, is this pair of electrons right here is going to reach out and grab that hydrogen atom. This arrow would represent bond formation. I'm making a new bond because I have a pair of electrons that used to just be associated with that oxygen atom that's now reaching out and is going to form a bond with that hydrogen atom. Okay, and then I also have to break that bond that I pictured in orange. Where are those electrons going to go? They're what's going to form that extra lone pair on that chloride ion. So again, the base of my arrow is going to start at that bond, at that pair of electrons, and it's going to pull that pair of electrons onto that chloride ion, onto the chlorine. So the one arrow would represent bond formation, and the other one represents bonds breaking. Okay, so take a step back a little bit and just kind of convince yourself that you can see how the one arrow represents bond formation, because you're starting out with a lone pair of electrons that was just associated with the oxygen, and now it's going to be associated with both the oxygen and the hydrogen, because that's what that arrow is doing. It's reaching out and grabbing that hydrogen. Likewise, you want to take a step back and convince yourself that you can see that the orange bond is breaking with that pair of electrons. That pair of electrons used to be shared between the hydrogen and the chlorine. I'm essentially snatching that pair of electrons from the hydrogen and putting it only on that chloride ion.
So when it's one arrow, it's an irreversible reaction, right? And when it's a double arrow, it's a reversible reaction, or no?
Yeah, this is yeah. So good question. That's absolutely true. So this actually, when we use the double-headed arrow, it's more represents a resonance structure. It's specific to resonance structures. This arrow here, yeah, it represents a reaction that goes pretty much goes 100% to completion. And then if we wanted to represent a reaction that is not going all the way to completion, that's more like in a balanced equilibrium, we would do this with this double-headed arrow, or with this type of arrow here. I think you'll also see it like this. I actually kind of, it's sometimes I just default to this type of arrow here because in theory, all reactions are in equilibrium with one another. But really, if you're being good, you would represent reactions that go mostly to completion with just the single-headed arrow. But this one up here is actually specific to resonance structures. These ones over here. So
Okay.
before we were talking about resonance structures, these structures where you just have movement of electrons within a single atom. And down here, we're actually going to a chemical reaction. Okay. Yeah, the arrow formalism is something that's it's not something that I'm going to be too picky about at this point. If you accidentally gave me a double-headed arrow, or if you gave me the wrong arrow, I really wouldn't be too upset about it. But that is the logic behind the arrows.
Okay. All right. Thank you.
Okay, so we're going to do another reaction here. And actually, if I'm being good, this is one that would be more in equilibrium. But again, I'm okay if you guys don't know that yet. All right, so I'm actually going to get rid of this so that you guys can. First thing we're going to do is go in and fill in our lone pair electrons. Okay, so everybody take a second, given what we have here, just given the number of bonds that you see represented, draw in the lone pair electrons and the formal charge for the nitrogen and the oxygen on both sides of my reaction here. All right, so nitrogen with one bond or with 3 bonds should have 1 lone pair. Oxygen with 2 bonds should have 2 lone pairs. Nitrogen with 4 bonds won't have any lone pairs, and it will actually have a formal charge of +1. And when oxygen only has 1 bond, it should have 3 lone pairs and a formal charge of -1. Okay, so that we could do, that portion we could do just based on those simple rules that we learned for a number of bonds that a particular element likes. And then if it has anything different from that, if it has more than that, it would be a positive charge. If it has less than that, it will be a negative charge. Okay, so hopefully based on what we did last time, you can see how I filled in those lone pairs. All right, now we're going to play the spot the difference game. What is the difference between these two sides of our chemical reaction? I want everybody to take a second and see if they can't identify which bond on the left-hand side is going to be broken and which bond on the right-hand side is going to be the new bond that's formed. All right, so this is my bond that's going to be broken. And then this is my new bond over here. This is the one that's going to be formed. All right. And then again, the cool thing, or at least if you're a chemistry nerd like me, you think it's pretty cool. The cool thing is that we're going to be able to represent these bonds being broken and these new bonds being formed using our electron pushing arrows. Okay. And notice that what's changing, so I'm breaking one bond and I'm forming a new bond. That means it's this hydrogen that was formerly associated with that water molecule is going to then be bound to that nitrogen. right? So that's what I have to represent, is that hydrogen moving over. So how I draw the bond that's being formed is this pair of electrons is going to reach out and grab that hydrogen. That's the formed bond. Okay, and everybody take a second and see if you can't draw me the arrows to break that orange bond. So this pair of electrons on that nitrogen is what now forms that new covalent bond. This pair of electrons is going to go from that chemical bond and then be associated only with that oxygen. So that's my bond that's being broken. Okay, so our electron pushing arrows represent the movement of the electrons in this reaction. Okay, so we're not quite through chapter 1 yet. We'll finish that off at the start of next week. I'm going to extend the OWL homework for the latter half of the chapter because obviously we haven't gotten through everything yet. It is a good idea to go ahead and try to take a stab at it, right? The other thing is I will have office hours. I have office hours on Monday. I'm also like more than happy to meet over Zoom outside of office hours. So if you're struggling and you want to go and like share your screen and show me what you're doing and all that good stuff, that's perfectly fine. Okay. I know it's going to be a little bit tricky. I know that organic chemistry in general is really intimidating. Again, a lot of what it is just, good question. So a lot of what it is just sort of keeping track of what we know right now and what we don't know. We don't know a lot about these chemical reactions or about these structures. What we do know is how to represent them, how to fill them in with the lone pairs and the charges. And now we can actually move electrons around and make new bonds as well as break old bonds. Okay. Yeah, we are going to go back on the 7th. So we have one more week of the virtual learning. They just extended it to the end of next week, and then we'll be back in person. We've been pretty assured that it's not going to be extended again. So after next week, we should be fully in person, which I know is a big relief for everybody because this is less than ideal. I mean, the commute's great. It took me 0.4 seconds to get here, but nonetheless, it's not ideal. Okay, so before you leave, do me a favor, throw your name in the chat, full name as it appears on my roster for attendance, and then I'm done with y'all, and I'll see you next week.
Have a good one.
Yep, you too. If you guys have any questions, of course, hang around and you're more than welcome to ask.